Hello everyone. Today we'll learn about the excitation system of synchronous generator. I am the main teacher today, Luo Qiang. In the last lesson, we talked about voltage control and controlling the distribution of reactive power. So next, we will talk about improving the stability of synchronous generator parallel operation. When analyzing power system, stability problems, whether static steady or transient steady, the mathematical model expression always contains the generator, no-load electromotive force, EQ factor, and the EQ factor is related to the excitation current. We can see that the excitation automatic control system improves the system stability by changing the excitation current, and thus the EQ factor value, the effects of excitation on static steady and transient steady, are analyzed respectively as follows. First, effect of excitation on static steady. There is a simple power system wiring diagram as shown, where generator G is through a step-in transformer, a transmission line, and a step-down transformer connected to the receiving end system. Suppose that the receiving end bus voltage U phasor is constant. The system equivalent network and phasor diagram are shown in Fig. The generator's output power is shown in equation, where X sigma is the total system reactance. Generally is the sum of generator, transformer, and transmission line reactance. Delta is the phase difference between the generator no-load electromotive force EQ factor and the receiving end voltage U factor, corresponding to a fixed value of no-load electromotive force EQ factor. Generator transmission power PG is a sinusoidal function of the power angle known as the synchronous generator. Power characteristics or power angle characteristics. It is well known that when the delta is less than 90 degree, represented by points A in the figure, the generator is static steady when the delta is greater than 90 degree, represented by point B in the figure. The generator cannot operate stably when the delta is equal to 90 degree. It is the limiting case of stability, so the maximum possible power transfer limit is Pm. The above analysis shows that the static steady limit power Pm is proportional to the generator, no-load electromotive force EQ factor, while the value of EQ factor is related to the excitation current. The generator power characteristic corresponds to a certain value of EQ factor, which is called the internal power characteristic curve, as shown in the curve A in figure. In fact, when the generator is equipped with an automatic excitation regulator, the static stabilized power angle increases. That is, the delta can be greater than 90 degrees to operate. Because when the active power PC of the generator output increases, the power angle delta increases. To maintain the generator's terminal voltage EC's phasor constant for the generator with the excitation adjusted according to the voltage deviation. The excitation current must be increased to make the EQ value higher, so that the operating point will be shifted to another internal power characteristic curve with larger amplitude. Similarly, the power angle delta increases further and the operating characteristic curve is higher, so that a cluster of power characteristics curves with successively higher amplitude is obtained, as shown in the figure, where curve B is an ideal power characteristic curve. Its power angle limit is greater than 90 degrees. The static stabilized power increases. for the proportional adjustment of the excitation control system, according to the deviation of the operating parameters, under the condition that there is no failure zone in the measuring unit. It is generally only possible to reach approximately the power characteristic shown in curve C in the figure. Its power angle limit is greater than 90 degrees. The static stability of the power increases. Because the excitation regulator can effectively increase the static steady limit of the system, it is required that all operating generator units should be equipped with an excitation regulator. Second, effect of excitation on transient steady. Whether the generating unit can continue to maintain synchronous operation after the power system has been suffered a large disturbance is the research subject of transient stability. Due to the rapidity of modern relay protection fault removal, the influence of the general excitation automatic control system on transient steady is not as significant as it is on the static steady, but under certain conditions can still be seen in its obvious effects. Let's take the example of a single machine to an infinite system. Suppose that under normal operation, the generator delivers power as PGO, operating at a point of the power angle characteristic. After a sudden disturbance, the operating point of the system suddenly changes from point A on characteristic curve 1 to point B on curve 2 due to the inertia of the power input part. The input power is still PGO, and there will be excess torque on the generator shaft, which accelerates the rotor. The operating point of the system moves from point B to point F along curve 2, passing point F. The output power of the generator is greater than PGO, so there will be a break-in torque on the rotor shaft, which will decelerate the rotor. Whether the generator can operate stably or not depends on the upper and lower areas formed between curve 2 and PGO. Whether the shaded areas are equal or not is known as the so-called equal area rule. In the above process, if the generator can be forced to increase the excitation to make the operating point of the disturbed generator set shifted to operate on the power angle curve 3, which not only reduces the acceleration area, but also increases the deceleration area, so that when the generator is swinging for the first time, the amplitude of the power angle delta is reduced, and the transient steady of the generator is improved. When swinging back, the excessive deceleration area is not favorable. Then if you can let it back to the point D on the characteristic curve 2 to operate, you can reduce the return amplitude, more favorable to the stability. The above extremely simple example makes us realize that under certain conditions, the excitation automatic control system can also improve the transient steady of the power system, if it can carry out some suitable control according to the requirements. According to the definition of dynamic steady, when analyzing the dynamic steady, it is more important to take into account the influence of automatic control system, such as excitation regulation. Fourth, improve the operating conditions of the power system. When the power system appears short-term low voltage for various reasons, the excitation automatic control system can play its regulating function. That is, greatly increase the excitation to improve the system voltage. First, after removing the short circuit, it can accelerate the recovery process of system voltage and improve the self-starting condition of asynchronous motors. When a short circuit or other fault occurs in the grid voltage decreases, which puts the motors of most users in a braking state. After the fault is removed, the motor needs to absorb a large amount of reactive power when it starts, so that it slows down the recovery process of the grid voltage. The generator impact exciter can accelerate the recovery of the grid voltage, effectively improving the operating conditions of the motor. Second, create conditions for asynchronous operation and self-synchronization of generators. When the excitation system of synchronous generator loses excitation, it needs to absorb a large amount of reactive power from the system, which causes the system voltage to drop greatly and even endangers the safe operation of the system in serious cases. In this case, if the other generating units in the system can provide enough reactive power to maintain the system voltage level, the generator without excitation can also be maintained in asynchronous operation for a certain period, which not only ensures the safe operation of the system, but also facilitates the operation of the thermal equipment of the unit. When there is a shortage of active power in the system, the standby hydro generating units are quickly put into the grid by self-synchronization, which is of certain significance to ensure the reliable operation of the system. However, when the generating unit is put into the grid with self-synchronization mode, it'll cause a sudden drop of voltage between the electricity, and then the other units in the system should increase the excitation current rapidly to ensure the recovery of grid voltage and shorten the process of the unit's parallelization. Third, improve the correctness of the relay protection device operation. When the system is in low load operation, the excitation current of the generator is not large. If a short circuit fault occurs in the system at this time, the short circuit current is small and decays with time, so the relay protection with a time limit cannot act correctly. The excitation automatic control system can adjust the generator excitation to increase the short circuit current and make the relay protection work correctly. It can be seen that the generator magnetization control system plays a very important role in improving the operating conditions of the power system. Fifth, meet the requirements of hydro generator units to forcibly reduce excitation. When the hydro generator unit fails and suddenly trips, because of its speed control system has a large inertia, cannot rapidly close the water guide vane, and thus will make the speed rise sharply. If measures are not taken to rapidly reduce the excitation current of the generator voltage may rise to the extent of the stator insulation is jeopardized. Therefore, in this case, the excitation automatic control system is required to realize forcibly reduce excitation. That's all for this lesson. Thank you.